Alice, I guess you could, well, I don't know which one represents N. Apparently Alice represents W. Alice has got A bits to communicate with to Bob, and somehow it wants to, I mean, the input, I guess, is of size W, right? That's the query. Bob, on the other hand, knows all the data, so it's, in some sense, represents the N side. It's able to communicate with B bits of information. So log base B of N, somehow enough to communicate N. It's not a great intuition for this, but at least it's nice and symmetric. Now let's work out what it actually corresponds to. This is a lower bound on colored predecessor. So for any colored, even static colored predecessor data structure, static, can be randomized, and this will be a lower bound on the expected performance. Okay, so what this implies for polynomial space, which is kind of the case we care about, for polynomial space data structure, A is going to be order log n. Okay, in fact, we only need A to be polylog n for what I'm about to say to be true. So then this becomes min log, I want n. I guess. Is that what I wrote over there? I don't even remember. I wrote log w. I guess I'm going to write log n. That's the right answer. Okay. Fine. So we get B is just W. So that's a log base W of n. That's just fusion trees. This one ideally would be log W, but we're off by this log factor if A is log n. Okay, that's the best we'll be able to prove today. So this is slightly less beautiful because it's both W and n, but so is this one. And this is not the true answer. The true answer has no log. Okay, but that's what we get from this nice symmetric bound for polynomial space. You can also use this to prove the beam-thick lower bounds, which I've by now erased, which are the for all n there exists a W, for all W there exists an n. Why don't I briefly cover that? So again, let's assume that A is order log n with polynomial space. Then the lower bound will be largest when the two terms in the min are equal. So log base A of W equals log base B of n. That's these two guys. So this is log W over A is order log n, so this is going to be order log n. And I want this to be equal to log n over log W. So we can cross multiply, get log squared W equals log n log n. And so log W is equal to square root log n log n. And let's see, you can also take logs, and from this conclude that log W equals log n. Right? The two I'm throwing away constant factors, and when I say equal here, I mean up to constant factors throughout this half board. Okay, so you take logs, you get 2 log log w on the left-hand side. Over here you get log log n plus log 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 n. So it's dominated by log log n. So in this scenario where these two things are roughly equal, you get log log w roughly equal to log log n. And so from this bound, or from this equality, we should get the old beam-thick bounds, which let me write them again. So they are we want to compute what was this bound. We have log w divided by log a, or log w divided by log log n. So log w divided by log log n, but log log n now is log log w. So this is going to be log w over log log w, which was one of the beam-thick bounds. So for all w, there exists an n such that omega, this thing, holds. Okay, on the other hand, we have log n divided by log w. Log w is now square root of log n log log n. So this is log n divided by square root of log n log log n. So the square root log n cancels with this. We end up with square root of log n on the top. And we keep the square root of log log n on the bottom. And so we get the other beam-thick bound, beam-thick Zhao bound. For all n, there exists a w such that omega, this holds. Okay, when you just need existence, then we get to choose the relationship between n and w however we want. So you don't have to believe me that it's largest when they're equal. Happens to be true, but the point is there is a choice of w and n, namely this choice, log w equals root log n, where you get a lower bound of this. And there's another choice for n versus w where this happens. Okay, so this implies the beam-thick Zhao bounds, but I kind of prefer this form because it's clear up to this log log n factor, we understand the complete trade-off between w and n, assuming polynomial space. Okay, so we're going to prove this bound, which implies all this stuff, using round elimination lemma. So we're proving this claim here. Omega min log base a of w log base b of n for any colored predecessor data structure. So let's suppose you have a colored predecessor data structure, and it can answer queries in T cell probes. Okay, which in the communication complexity perspective, that's rounds of communication for colored predecessor. Our goal is to do T round eliminations. Okay, slight discrepancy in terminology here. Round elimination lemma is really about eliminating one message, which is half a round. But you do it twice, you will eliminate a round. And so we need to do 2T calls to this lemma. We will eliminate all messages. Then there's zero communication. Then the best you could hope to do is by flipping a coin. Maybe you're worse than that. But the error has to be at least, probability of error has to be at least a half. So we'll either get a contradiction, or we're going to set things up so the error is at most a third, and therefore this will prove that t has to be large. So you couldn't eliminate all the messages. Anyway, we'll see that in a moment. So we have a setup like this, and in our case there's this picture. There's an asymmetry between Alice and Bob. I mean, yeah, the picture's nice and clean, but in reality, this has to represent a colored predecessor problem. So in reality, Bob is a data structure and is not very smart, just does random access. Alice, we don't know. I mean, it could be very smart. And Alice just has a single word. So there's an asymmetry between Alice and Bob. So when we eliminate a message from Alice to Bob, it's going to be different from eliminating a message from Bob to Alice. This f to the k thing here is going to have to be different when we're doing an Alice to Bob message versus doing a Bob to Alice message. And that's where we're going to get a min. When we go from Alice to Bob, we're going to be essentially contributing to this term. When we go Bob to Alice, we're going to be contributing to this term, I think, or the reverse. We'll find out in a second. So let's do first Alice to Bob. Because that's the first type of message we need to eliminate. So let's suppose, now as we eliminate things, W and N are going to decrease. So I'm going to suppose at this point, Alice's input has W prime bits left. Okay, initially W prime is W, but I want to do the generic case so I don't have to repeat anything. Okay, here's the concept. Remember, we're proving a lower bound. We get to set up the set of elements however we want. We're going to define a distribution on the set of elements. And we're going to do that by breaking this input, W prime, bits, into a lot of pieces. Okay, Alice's input you think of as X. I don't necessarily want to call it X. Well, sure, we can call it X. There it is. What I'd like to do is break that input into chunks, x1 up to xk. This is basically what round elimination tells me I should do. If I want to view my problem as an f to the k problem, somehow my input is not just one thing, it's k things. Well, in reality, the input is a single word. So I'm going to have to split it into subwords in the usual way. Right? Van den Bosch would split it in half. We're going to split it into more pieces because we need to guarantee that this error is small. We need k to be large for this error to be small. Okay, I claim this is the good choice of k. And so now this is x1, this is x2, this is xk. The low order bits are xk, the high order bits are x1. Or the reverse, it doesn't actually matter. Okay. So why is this a good choice of k? Because if we then look at the error increase we get from here, error increase is square root of a divided by k. So error increase, which is order a over k, is going to be, k is now this. So the a's cancel, and we get, square root of a over k. A over k was the wrong analysis. Square root of a over k is the correct bound. Still the a's cancel, so k has an a factor. And so we get order square root of 1 over t squared, also known as 1 over t. Okay, this is good. And there's a constant here. And if I tune all this constant correct, I can make this constant less than a third. And so if I start with a protocol, let's say that's completely correct. You don't have to. You can start with one that's correct with at least probability 3/4 or something. But let's just say, for simplicity, the initial data structure is completely correct. if every time I do an elimination of a message, I guess I should set it to be 1/6 times 1 over t, and I do this 2 times t times, in the end, the error will be only 1/3. So I'll be correct with 2/3 probability. Okay, so never mind the constants. I can set this constant right. So this is some epsilon times 1 over t. So after I do this 2t times, I end up with an error that's only epsilon, or 2 epsilon, or whatever. So that would be a contradiction. So that's why this is a good choice. I'm basically balancing the error I get from every message elimination. I want them all to be order 1 over t. So it's nice and balanced. That will give me the best lower bound, it turns out. Okay, but what does this mean? I mean, somehow, I have to have an f to the k problem. Meaning, really, I should only care about one xi here. That all the interesting stuff is these bits. But Alice doesn't know which is I. Only Bob knows which is I. What does that mean? Bob knows the set of elements in the data structure. So basically, the set of elements maybe they all differ in these bits, or maybe they all differ in these bits, or these bits, or these bits, but only one of these. So that's a distribution of inputs. Okay, there's one class of inputs where they all differ in the x1 part, but then they're identical for the rest. There's another, for each xi, there's a set of inputs where they all differ in the xi's and nowhere else, let's say. But Alice doesn't know which setting she's in. Alice just knows x. And so Alice is kind of in trouble because you can only send a few bits. You can only send a bits out of this thing, so you can't communicate very much. Let's go. I don't know what to erase. Get over here. I need the bound, don't need the corollary. So let me draw a picture for Alice, or for what the data looks like. So there's some initial segment which is shared by all elements. Then they all differ in this middle chunk. And then they all have, I don't really care what they have after that. So these are the elements in the data structure. And this is our usual picture of a binary tree, except I didn't draw it binary. I drew it with some branching factor so that the height of this tree is theta at squared. So I set the base of my representation so that you branch whatever, w divided by at squared. Here, that's my branching factor. So cool, that's my picture. And this is depth I. So Bob knows this picture. Bob knows what all the elements are, so he can build this picture or whatever. Bob knows which is the relevant depth that they differ. But in the lower bound, we're going to say A is chosen uniformly at random. So Alice has no idea which bits to send. And so probably, Alice is going to say, oh, here's, I know these bits. But Bob already knew those bits, so Bob learned nothing. And so that's why you can eliminate the round. That's the intuition, anyway. The proof is, well, you just apply round elimination. You see that the problem now becomes to compute predecessor on this node. Just like in fusion trees, at every step of the way, the hard part was to compute predecessor at the node. Here, if Bob is allowed to do computation, then really Alice just needs to say what are the things here, or together Alice and Bob somehow have to figure out what is the predecessor at this node of xi. Which way the query goes, which could be in between one of these, that is xi. The rest of the xi's of the xj's don't matter. Only xi matters. And so the problem reduces to computing predecessor here, and that matches the definition of f to the k. So we have successfully set up an f to the k problem. The only thing you need to do to solve the overall predecessor problem is to find your predecessor in the node, because there's only one element within each subtree. That's enough to figure out your overall predecessor. Okay, if you could make, yeah, fine. Okay, depth I, at squared. I guess you can think of this as y. That's the part that Bob knows. These are in some sense x1 up to xk minus 1. And this is why we had to say over here that Bob already knew x1 up to xi minus 1. Because Bob already knows that the shared prefix among all the items. So, sorry, not k minus 1, I minus 1. And so all the content is here in this node, which is y. And so it reduces to a regular predecessor problem, which is what f will always denote, colored predecessor of xi comma y. Cool. OK, what happens here in terms of n and w? We have a smaller problem here, right? We threw away all this stuff. What got reduced is our word size over here. We started with something of size w prime. And now we end up with something of this size, which was w prime divided by at squared up to theta. Okay, so this reduction reduces, or this round elimination reduces w prime to w prime divided by at squared, theta that. Okay, I think that's all I need to say at this point. The claim is that this picture is kind of like Van de Boas, okay, in the following sense. Van de Boas is essentially binary searching on which level matters, right? If it goes too low, things are empty. If it goes too high, there's too many items. So it's binary searching for that critical point where you basically, you have a predecessor and you have a node and nothing else. And that's why I took log W. So here, one level matters. And the goal is to figure out which one. And it's not exactly binary search here. We're losing a larger factor, at squared, at each step. So we're not reducing w to w over 2, like we did with Van de Boas. But, and this is why we're losing a little bit, we reduce by a factor of at squared. So it's kind of like the Van de Boas upper bound. But here, we're setting up a lower bound picture so that this is still an arbitrary predecessor problem. But figuring out which level matters, that's tricky. And you really can't do much better than Van de Boas style binary search. Okay, maybe you can do at squared way binary search instead of binary search. But okay, so that was eliminating a message from Alice to Bob. Eliminating a message from Bob to Alice is going to look like fusion trees. That's the cool thing. So let's do that. Page. Okay. Let's suppose, so this is going to get slightly confusing notationally because you have to reverse A and B. The picture I set up over here, and for the round elimination lemma, f to the k and round elimination lemma are all phrased in terms of eliminating the Alice to Bob message. You've got to invert everything. So we're going to get square root of b over k error if I don't relabel things. So you can restate this. If Bob speaks first and then Alice speaks next, you get square root of b over k error. The f to the k problem is now that Bob has k inputs. Maybe call them y1 to yk. Alice has an input x and the integer I. So now Alice, the querier, knows what I is, but Bob doesn't. The data structure doesn't know it. Okay, so just reverse everything. So let me state it over here. Bob has an input. Now in general, it's what Bob knows is a bunch of integers, n integers. In general, n prime integers, because n is also going to increase. And let's say each of them is w prime bits. Okay, that's what Bob knows. That's y. Okay. So what do we have to do to phrase an f to the k problem? Well, just like this, we've got to break that input into bt squared equal size chunks. So let's just think about what that means. So it's going to be y1 up to yk. K is theta bt squared. Again, we want bt squared because then you plug it into this root b over k formula, and you get that the error increase is order 1 over t, which is what we need to do t round eliminations. So now, before our input was a single word, now our input is a whole bunch of integers. So it's natural to split it up into different integers. Okay. Here's how I'm going to do that. I'll just draw the picture over here. So this was the Alice to Bob elimination. Now we'll do the Bob to Alice picture. So what I'd like to do is split up all the inputs. What's the natural way to do that? Well, have a tree at the top. Let's just make it a binary tree. So I'm drawing the usual picture I draw when I draw a bunch of elements. And fine, then there's some elements left over in each of these subtrees. Each of these is a predecessor problem. Okay, I'm constraining the inputs to sort of differ a lot in the beginning, in the early bits, the most significant bits. This is the most significant, next most significant, and so on bits. I want the number of leaves here to be theta bt squared, or not leaves, but number of intermediate nodes here. And therefore, there are theta bt squared subtrees. And I want to set up the n items to be uniformly distributed. So each of these has n divided by bt squared items. Okay, so we used a few bits up top here. How many bits was this? Just log of bt squared. So if you look at one of these subproblems, we have reduced w slightly, but only by this additive amount. Okay, it basically won't matter. The big thing we changed is we used to have n items to search among, or this is n prime, I guess. Now we have n divided by bt squared items. So we reduced n substantially. And this is what fusion trees do, right? They look at the root first and say, okay, look, I can distinguish w to the epsilon different things in constant time. Okay, here it's not w to the epsilon, but it's bt squared, and we haven't figured out what b and t are yet. So, I mean, b is w, so that's close to a w factor, w-fold search. And then you determine, am I in this subtree or this subtree or this subtree? This is exactly what fusion trees do. Okay, but we're setting up a lower bound instance where that is the right thing to do, where you have to know what the early bits are before you can figure out which subtree you're in. Okay, now reverse roles. Alice knows what these bits are. The data structure of relevance, let's suppose you fit here because you are 0, 1, 1 in the beginning. Okay, this is our yi problem. Alice knows what I is. Alice knows what those leading bits are. Bob doesn't. And Bob's speaking first. So Bob could try to summarize this entire data structure, but there's basically no hope, right? Bob needs to know what are those early bits. So the first message from Bob is going to be useless. Alice can then send the bits, and then you can restrict your problem to a regular predecessor problem in here. So if you eliminated this sort of root node, your entire problem is a predecessor problem in here. So again, we have an f to the k style problem. We reduce to a predecessor problem on a smaller, in this case, y and x are reversed, but we end up with a smaller problem, mainly in the fact that n got smaller. So let me go back to this board. What happens is that we reduce n prime to n prime divided by bt squared. Thank you. There's theta. We also reduce w prime. W prime becomes w prime minus log bt squared. Okay, but in particular, this is going to be at least w prime over 2 most of the time till the very end. And over here, we're reducing w prime by a big factor, something bigger than a constant. So we don't really care about losing a factor of 2 because we alternate between these. And so a factor of 2, just falls into the theta. So it's going to be at least that as long as w prime is, I don't know, at least log, what do I want to say here? Log w would be enough. Yeah, this is log w. T squared is going to be at most log w. So it's this is going to be log w plus log w. Log w goes away. Okay, what is t? The whole point is to prove a lower bound on t. But we know from an upper bound perspective, t is at most log w because Van of Debose exists. So we're never going to prove a lower bound bigger than log w. So whatever t is going to be is at most log w. So this is just log w. So you're fine. Okay, but at some point we have to stop. Okay, we start with some w and n. N prime is racing down at this rate. W prime is racing down at this rate. When w prime gets down to log w, then we're in trouble. If n prime gets down to 2, 1, 0, one of those constants, when n prime gets down to a constant, we're in trouble. You can no longer evenly divide things. Okay, so when does that happen? That's when, this is where we're going to get a lower bound. Okay, so I guess we can go back over here. We have to, so if you do a round elimination, you decrease w prime by this factor, and you decrease n prime by this factor. Do both of these in sequence. Then you repeat it. So we have to stop when w prime hits log w, or when n prime hits 2, let's say. This is not really going to make a difference. You can also think of that as 2. In fact, I'll just do that, just to clean the arithmetic a little bit. Fine. Now, if we succeed in eliminating all the messages, we get a contradiction because we set up our errors to add up to only 1/3. And we know that the error has to be at least 1/2 if you eliminate all the messages, which means we didn't eliminate all the messages. Now, we will not eliminate all the messages if t is large. So when would we eliminate all the messages? Let's compute that. And then t has to be at least that big. Right, t has to be at least has to be greater than the point at which we would eliminate all the messages. Otherwise, we get a contradiction. So this is where we get a min, which is kind of cool, because we have to stop when w prime gets too small or when n prime gets too small, whichever happens first. And so it's going to be a min of the thing relating to w, which is going to be log base at squared of w, because we're reducing w by a factor of at squared each step, so that's when it's going to bottom out. And then there's the thing for n, which is log base bt squared of n. That's when n will bottom out, because we're reducing by a factor of bt squared each step. Okay, so that's the bound we get. Now, it doesn't look quite like the bound that we want, which is this very simple log base a of w, log base b of n, but I claim that it's basically the same thing. Why? I'm going to cheat here, speed things up a little bit. I claim that at squared is order a cubed. Why? Because a is at least log n. Remember, a is log of space. You've got to have, you have to be able to, you have to store the data. So you need at least n words of space. A is log of that, so it's got to be at least log n. And furthermore, t is at most log n. Why? Because there is a predecessor data structure that runs in log n time per operation, namely balanced binary search trees. Okay, there's a theta here, or an order, big O. Okay, but AT squared is at most A cubed. Okay, on the other hand, this thing, BT squared, is order B cubed. Why? Because T is order log W. B is W. That's the definition of B. T is order log W because Van Em-de-Boos exists. And so this is actually at most W times log squared W. But in particular, it's at most W cubed. Okay, and that we don't care about that constant because it's in a log. So it just comes out as a factor of a third or whatever. And so this is the same thing as log base A of W log base B of n min. And that's the nice symmetric bound that you get out of round elimination. Pretty cool. Now, if you look in the notes, I'll just mention this briefly. There's a couple more pages that give you a little bit of flavor of what the round elimination and that vague proof sketch, which gave the wrong answer by a square root, really means. We said, oh, Alice can only communicate, in some sense, A over K bits about xi. And you can formalize that by talking about distributions of inputs and talking about the expected amount of entropy of xi communicated by that first message. And so it's very simple definitions of entropy and shared information, but just in terms of probabilistic quantities. And it at least gives you a sense of how you might prove something like this, whereas talking about information about something is kind of vague. Talking about entropy, which is about sum of probabilities times log of probabilities, is a clean probabilistic notion. So it becomes a purely probabilistic statement and about error probabilities, and that's how you argue this. But even these notes do not give a proof. They just give a hint of how you formalize what this means, or what the proof sketch means. And then you have to do, it's several pages to actually prove it, so a bit beyond this class. But once you have it, because it's very clean, I'd say kind of beautiful lower bound, not quite the right answer, but up to log factors, the right answer for predecessor. So, and that's the end of predecessor in this class.